Hey guys, welcome back to Business Statistics. This is going to be a section 7.3, interval estimate of the population mean with an unknown population standard deviation. Okay, that is code for we don't have a population standard deviation. So we're not going to have a sigma, we're only going to have an S. Okay, and what that ultimately is going to mean that we can't use z-tables to solve things. We're going to have to use our t-tables, our t-distribution. So this should be the first time that you guys have seen this. So yeah, but it's going to operate very similarly, very similar concept. But the table, the way that you find the values is going to be a little bit different. But the concept is very, very similar. All right, so let's walk through it here. Estimation of sample mean when the population standard deviation sigma is unknown, the circumstances when t-distribution is used. So the circumstances I just talked about, the circumstances when the t-distribution is used is when we don't have a sigma. We're not given a sigma, meaning we're not giving the population parameter of standard deviation, okay? So then what that means is what we will have or what we will be able to calculate is a sample standard deviation or a sample standard deviation. We'll either be given that or we'll be able to calculate that. So that's denoted as S. Okay, the similarities and differences between the t-distribution and the z-distribution. They're both bell curves. They both are symmetrical. They both are effectively centered around the mean. Okay, you can see here in the red that the standard normal is taller than all of the t-curves, and the t-curves or the t-distribution, there's an infinite number of them. Okay, whereas there's just one standard normal curve, there's an infinite number of t-curves, and these t-curves approach the normal curve. They get taller and taller and taller, approaching the normal curve all the way up into infinity. Okay, so they're flatter for n values that are lower, and they're taller for n values that are greater. Okay, so as you get to like a really tall n value, you start to approach something that's going to look like the normal curve, and thus the t values that you obtain start to look like z values. So the formula for confidence interval when sigma is unknown, so this is just the formula for the confidence interval that we would use in the scenario that we're talking about right now, is very similar to that of when sigma is known. Okay, so the formula, as you can see on the screen, is x bar plus or minus t alpha half times s over the square root of n. If you think back or scroll up, or I guess you're probably not following along via the Word document, you probably printed it off. But if you turn back to the page of the confidence interval where sigma is known, you'll see that it looks like a very similar confidence interval formula. It should be x bar plus or minus z alpha half times sigma over the square root of n. So just as we don't have a sigma in this sort of scenario, we can't use sigma, so we use S. Okay, and because we don't have sigma and because we're using S, we use a t statistic and not a z statistic. Okay, finding critical values, that's what we're going to do here when we solve this problem. And the formula for the margin of error, well, that's very similar as it was in the last one. The formula for the margin of error is just what we have listed to the right of the plus or minus. So that's just our t alpha half times s over the square root of n. Okay, so let's get to our example. All right, an executive in a large bank is looking for some estimate of the average mean credit card debt for all U.S. households. She found a representative sample of 25 households with credit card balance information. Using this sample, she obtained a sample mean x bar equal to 9312 and a sample standard deviation s equal to 4007. Assume that credit card debt of all U.S. households is normally distributed. She is interested in a 95% confidence interval estimate of the average mean credit card debt for all households. Okay, so this problem is exactly the same way that we just solved the z confidence interval problem, except for one thing. Except that we don't have a sigma. So we need to use our formula for S. Okay. Let me get this pen to work. Yes, it's working. Okay, so the first thing that we start off by doing, and how I start every problem, is I'm going to write down that which we know. All right, we have a sample of 25, so n equal 25. X bar equal to 93. What on earth? What is going on? I do not know what it is doing. Okay, I'm just going to leave it go, and S equal 4007. Oh no. Oh no. Alright, and then the other thing that we know is our confidence interval is equal to 95%, which then that implies that our alpha is what? 0.05. Okay, just 1 minus our confidence interval. And so then thus we know that our alpha half is 0.025. Oh, another thing too, and I should write this, when we work with t characteristics, our t alpha half is actually t alpha half, comma, df, comma, our degrees of freedom. Okay? And degrees of freedom is a very simple thing to calculate. It's just n minus 1. Okay, so this is going to help us when we go to look in the in the table to find our values. So we know we're doing a confidence interval. So we can write our x bar plus or minus our t of alpha half, comma, df times s over the square root of n. So we know that. So that's written up there. So, but I just like to write this out as a, let's check to see what we have. Do we have an S? Yes, we have a 4007. Do we have an N? Yes, that's our 25. Do we have an X bar? Yes, we do. The only thing we don't have is this T alpha half, comma, DF, right? But we know how to find that. We are going to use our alpha, and we're going to use our degrees of freedom. Okay, so this then becomes, this is going to be our T of 0.025, because that's our alpha half, comma, our degrees of freedom, which is n minus 1, so 24. So this is what we're going to be looking for in our table. Okay, so I just pulled up our table. Now we have to scroll down to t distribution, which I believe is right after the z. Yes, so it is right after the z, and this table operates a little bit differently. Okay, we have to go and we have to scroll over to whatever our t alpha half is. So we had a t of 0.025, so it's right here, this column. We're looking in this 1, 2, third column right here. And then we have to look for our degrees of freedom. So our degrees of freedom was 24. So we're at 24, third column, 2.064. Okay? So we hop on over to our sheet. So we then say this is equal to 2.064. Okay, so we now can make our statement. I wish I would have left myself a little bit more room to write here, but we'll make it work. 9312 plus or minus 2.064 times 4007 divided by the square root of 25. And I am just going to tell you what the answer is rather than working out the arithmetic because I don't have room. And our answer is 7661.12 and 10,962.88. All right, so what does this mean? So we need to be able to interpret this. Okay, so we have, first of all, we have an interval, right? So we have a range, or well, let's not call it a range. We have an interval. All right, we have some number to some number. All right, we have 76. We have roughly 7661 and roughly 10,963. Okay. So what are we saying here? What does this interval stand for? Okay. This, just like the z interval that we did, okay, is the confidence interval for which we believe mu lies. Okay. So I'll say that again. So this is the confidence interval that we believe mu lies in. Well, how sure are we that mu lies in there? We're 95% certain. So this is our 95% confidence interval that mu is between 7661 and 10963. Okay? That's the whole point of this. The whole point of this is we're trying to figure out, like a really good estimate for mu. So, we could view x bar and we could say, well, x bar, the sample mean is an estimate for mu. Well, that's certainly right, but we want to know with some level of certainty. We can't just take 25 U.S. a random sample of 25 U.S. households and say, well, that's just gonna have to do as our estimate for the 200 million U.S. households. So, but what we can do is we can say, we can create a confidence interval that we are 95% certain that the credit card debt resides in. So we're 95% certain now that the U.S. household credit card debt, or average U.S. household credit card debt, is between 7661 and 10963. Okay, guys, let me know if you have questions on that. This concept of confidence interval doesn't change from Z to T. The only thing that does change is the table that we use and the numbers that we have in order to calculate it. So this is a more real-life scenario in that, we can't assume that we know some population characteristic about this. So we have to say, well, we only know our sample characteristic, which is our S, which is our sample standard deviation. So this is a more realistic example. Okay? All right, let me know if you guys have questions. On to the next video.